It's a great pleasure for me to introduce the first keynote speaker, whom I know for many years, Professor Eyke Hüllermeier. He's a full professor at the Institute of Informatics at Ludwig-Maximilian University in Munich, LMU. And he also has there the chair of artificial intelligence and machine learning. So he studied mathematics and business computing, received his PhD in computer science from Paderborn University in 1997, with which he is, I guess, still connected, and a habilitation degree in 2002. Prior to joining LMU, he held professorships at several other German universities, like Dortmund, Magdeburg, Marburg, and also Paderborn, and spent 2 years as a Marie Curie fellow at Toulouse Institute of Computer Science Research. His research interests are centered around methods and theoretical foundations for artificial intelligence, with a specific focus on machine learning, preference modeling, reasoning under uncertainty. Besides, he's interested in applications of AI methods in other disciplines, ranging from natural sciences and engineering to humanities and social sciences. So he has published more than 400 articles in top-tier journals and major international conferences, and several of his contributions have been recognized with scientific awards. So yes, I checked his Google Scholar profile, which actually shows 612 positions with almost 18,000 citations. I think pretty impressive. And I said that he's still connected with Paderborn because from what I know, he's also a football fan and a die-hard supporter of SC Paderborn team. Okay, welcome, Eyke. The floor is yours.
So thank you very much, Wojtek, for this very kind introduction. And also thanks to the organizers for inviting me here. It's really a big pleasure to be here at this very interesting event. And I have to say I'm really quite impressed by the organization. So your students are really doing a great job here, so very professional. So, can you show my slides? Oh, I need to. Okay, good. Okay, so very good. The topic I'd like to speak about today is uncertainty in machine learning. And this topic of uncertainty in machine learning has received increasing attention in the last couple of years for obvious reason. The reason is that machine learning methods, like AI methods in general, are nowadays used in more and more practical applications in real life. I don't need to tell you, this conference is about applied machine learning. And many of these applications are actually what we would call safety critical. Yeah? So here is a typical example, medical diagnosis. What you see here is a standard scenario of what we call supervised learning. You are given some training data. In this case, it's X-ray images labeled as positive or negative, for example, whether a certain disease is present or not. And from this training data, a machine learning algorithm induces a model that could be a neural network, but could be in principle any other sort of machine learning model. And hoping that this model will generalize beyond the training data given, you can now feed it with new query instances, new X-ray images, for instance, of new patients, and the model will give you a prediction. So this is what we call a predictive model. And the prediction should not be just yes or no, positive or negative, for obvious reason. You would like, or perhaps the medical doctor would like, to have also some sort of information about how certain or uncertain the predictor actually is. So what is standard these days is that these predictive models will give you a probability distribution. Yeah, so here, in this case, the network may predict 0.8 for positive, 0.2 for negative, 80% probability of positive. Question is, how much can we actually trust these numbers? how precise, how accurate is this predicted probability of 80%. There are many more applications of that kind, which, as I said, we would call safety critical. In autonomous driving, for example, this is taken from one of the projects we are currently working on. This is a PhD student of mine. The problem is here, or the task is here, to predict, given a camera inside the car, where the driver is currently looking at, and which part of the car, and so on. Yeah. So autonomous driving certainly is another good example of a safety critical application of machine learning. Now coming back to this question, how much can we actually trust these numbers? What you see here are two examples, hand-picked of course, but making the point, I think, that quite often we can't really trust these predicted probabilities. So what we did here is we trained state-of-the-art neural network on ImageNet, a large collection of image data, and we applied the trained neural network to these images here as input. For the left image, the prediction was typewriter keyboard. For the right image, the prediction was stone wall. And obviously these predictions are wrong. Okay, that is not so bad because mistakes can happen. Even we as humans, we do make mistakes. But what is really not good is that actually the neural network expresses quite a high degree of confidence. In the left case, it's more than 80%. In the right case, it's even almost 90%. So that's not so good. At least we would like to see that in such cases, the network is telling us, I'm not actually so sure. But it's pretending to be quite confident. And this is actually not what we want. We could say that the predictive model is not very uncertainty aware. It's not so aware as it should be of its own uncertainty. It probably does not really know what it doesn't know, and this is not good in practical applications for obvious reasons. All right, so what can we do? Well, how can we do better? One thing is we could try, of course, to make better probabilistic prediction, to predict better probabilities. There is currently work going on in machine learning which is called calibration. This paper here is a quite nice recent survey paper on this topic. And what we try to do in calibration is to calibrate the predicted probabilities in a post-processing step, so to make them better calibrated. Indeed, many standard machine learning methods have a tendency to produce biased predictions of probabilities. Neural networks actually are not doing so bad, but if you look at simple machine learning methods such as decision trees, for example, they have a tendency to produce extreme probabilities. So they are biased toward the extremes for obvious reason, because if you know about how a decision tree is trained, it's actually trying to partition the instance space in such a way that the regions are becoming as pure as possible. Only positives, only negatives. So what we eventually end up with is probabilities that are biased toward the extremes. This is what you see here on the left-hand side, where I plotted the true probabilities against the predicted probabilities. And here you see a clear trend toward the extremes. Ideally, all the points here are lying on the diagonal, or close to the diagonal, meaning that the predicted probabilities are very close to the ground truth probabilities. What you see here on the right-hand side is another example where we have a systematic overestimation of probabilities, a systematic overestimation of the positive class. So here I'm always in the binary case so far, right? Okay. So the obvious idea now is to say, okay, if we do have these biases in predictions, let's try to get the points closer to the diagonal, right? What is one problem, one obvious problem here? Why in practice can't you simply look at these kind of diagrams? Because you don't know the ground truth probabilities. Yeah? In practice, you simply don't observe ground truth probabilities. What you do observe is the outcome. In the binary case, you observe positive or negative. So this is what we actually have to deal with. And I will come back to this on the next slide. The standard definition of calibration that is currently used in machine learning, but also in other fields, actually this definition comes from other domains, is given here. We call a predictor, a classifier, calibrated if the probability of an outcome y, given that the predicted probability of that outcome is alpha, is equal to alpha. Yeah? So as an example, among, or let's say 30% of all the days for which the probability of rain was predicted 30% is indeed raining. Yeah? So that would be a calibrated predictor. Please note that the conditioning is done here not on the query instance x. So for example, not on the particular day x or so, but the conditioning is done on the predicted probability. So it's not what we call in machine learning, it's not what we call per instance prediction. So it's not really a probability that is specifically tailored to one particular instance, which is actually the desirable thing. Yeah, if you think of medical diagnosis, for example, ideally the patient would like to have an uncertainty estimation that is specifically tailored for him or her. Okay, so as I said, in practice we don't observe ground truth probabilities, so we have to do calibration based on the binary data in the case of binary classification, or in general the data we have at hand. And different types of methods have been developed for that purpose. All these methods are basically trying to learn or fit a monotone transformation. Yeah? We would like to transform in a monotonic and typically nonlinear way the predicted probabilities in order to obtain improved probabilities. So here you see how the data typically looks like. We have the predicted probability on the x-axis, and on the y-axis we just have the label 0 or 1. Yeah. The step function here, this could be a fit that is obtained by what is called isotonic regression. This is one standard method that is used in this context. And the blue function here could be transformation that is learned by what is called beta calibration, a method that has been recently proposed by Marie Curie and some of his co-authors. And there are various other methods around. So as I said, I don't have the time to go here into detail. Today I would like to rather give you more kind of overview of what's currently going on in this field of uncertainty in machine learning. Yeah, so calibration, this is currently a relatively hot research area, I would say. And you can imagine that calibration becomes much more difficult for the multi-class case, or even for the continuous case if you would like to calibrate, for example, a regression model or whatever. So this is just the binary case, which is already difficult enough, but the problem becomes even more challenging in the multi-class case. Okay, so this is one thing we can do. We can try to improve our probabilistic predictions. So what else can we do? We could say that maybe it's not a bad idea to go a little bit beyond these probabilistic predictions and allow the learner to express its uncertainty on a say, kind of meta level, on a second level. What I mean is the following. So what you see here, now maybe first of all I should say that these triangles here, these triangles here, this is simply a projection of the probability simplex. This is called a barycentric coordinate system. So this triangle here is a projection of the two simplex. So every point, we are dealing here with a problem where we have three possible outcomes. So it's a three-class classification problem. Wojtek said I'm a football fan, so I took the example of the outcome of a football match here. Yeah? So you can think of predicting the outcome of a football match, whether it's a win, loss, or a tie. And every point in this triangle here gives you a probability distribution. So it gives you three probabilities: a probability for win, a probability for tie, and a probability for a loss. Now, we can assume that the ground truth is a condition, is a probability, so a point in this triangle here, because before the match starts, you simply can't deterministically predict the outcome. You cannot know, but there is a certain probability for the three possible outcomes for the three events. The type of machine learner with the lowest degree of uncertainty awareness is a deterministic predictor, which just predicts one of the three outcomes. So one of the corner points here, the red corner points. It is totally uncertainty unaware. Yeah? It does not take any uncertainty into account, simply claims that it can predict the outcome of the match. Certainly not what we want. We've already been speaking about probabilistic predictors, which are more uncertainty aware, aware of the fact that the ground truth is a probability distribution, and this learner will predict a probability distribution, for example, the red point here. But clearly the red point will be a little bit off, so the learner will probably not manage to precisely predict the ground truth distribution, which is the green point here. So what we maybe should allow the learner is to somehow represent this uncertainty about the probabilistic prediction. So we could allow the learner to deliver a prediction that I call second order prediction here, which could be different things mathematically. It could be what is called a creedal set in the uncertainty literature, simply a set of probability distributions. Yeah, this red region here. It could also be a second order probability, so it could be a probability distribution on the probability distributions. Yeah, so a probability distribution, a density function, for example, on this probability simplex. It could be different things like this. Such a learner would be more uncertainty aware. It would be more aware of its own uncertainty. The important thing is that this uncertainty here in the middle is not reducible, so we can't get rid of it. It's the assumption that the ground truth is a probability distribution. We don't have a deterministic dependency between inputs and outputs. This uncertainty here on the right-hand side, this is what we can get rid of, or at least reduce. Yeah. So, for example, when I ask you about the outcome of the next match of my favorite team, you will have no clue, because it's not a really famous team. It's just Germany's second league, and probably you do not even know Paderborn, and do not even know the competing team. So what would you give as a prediction? You could say, wow, I have no clue at all. I do not even know the teams. So I'm giving you the entire triangle, which means I consider all probability distributions feasible candidates. If I ask you about Poznan, you are probably more informed, and you can at least give a smaller region, so you are more certain about what are plausible probability distributions and what are less. But if I give you an opportunity, for example, to inform yourself about German football and so on, you can look at the recent outcomes of the recent matches, you can look at the tables or where they are currently standing and so on, you might be able to reduce a bit your uncertainty. So this leads to this distinction between what we call aleatoric and epistemic uncertainty, and this is a very important point. By aleatoric uncertainty, we understand uncertainty that is inherent. It's due to inherent randomness of the underlying data generating process. By epistemic uncertainty, we understand uncertainty that is due to a lack of knowledge. Yeah, it's a property not of the data generating process, it's a property of the learning agent. This distinction, I try to illustrate it here with a very simple example. The prototypical example of aleatoric uncertainty is coin flipping. You flip a coin and for sure you can't deterministically predict the outcome. If it's a fair coin, the probability of landing heads and tails is both 1/2. It's inherent randomness and you can't get rid of it. You can do what you want. You can't do better than predicting 1/2, 1/2. If I ask you, what is the meaning of the word Kichwa in the Swahili language, is it head or tail? You can be sure it's one of the two. And if I ask you, you will also be maybe as uncertain as in the case of coin flipping. However, you can get rid of this uncertainty just by Googling or looking up in the dictionary and so on. Yeah? So this is an important distinction to make, and this distinction is not at all new. It was already pointed out, for example, by the great statistician Ronald Fisher, who said, not knowing the chance of mutually exclusive events and knowing the chance to be equal are two quite different states of knowledge, and perhaps it's not a bad idea to make this distinction also in machine learning. And in machine learning, this distinction, okay, here I just repeat what I already said. By aleatoric uncertainty, we understand inherent uncertainty, uncertainty due to inherent randomness, which is irreducible, and by epistemic uncertainty, we understand uncertainty due to a lack of knowledge, which in principle is reducible. And this distinction is certainly, I would say, also relevant in machine learning, where uncertainty in a prediction, so most of the time we are interested in predictive uncertainty, the uncertainty in a prediction made by a learner. This uncertainty for sure depends on many things, and first of all on the amount and the quality of data that the learner has seen so far. So, for example, if you have seen a few positive and a few negative examples, and you are supposed to make a prediction at this point here, you will certainly be uncertain. Why? Because in that region here, for instance, you haven't seen much data points so far, and also overall you haven't seen much data. In this situation here on the right-hand side, you will also be uncertain when having to make a prediction in the same point, but now the situation is a bit different. The uncertainty in a sense is confirmed. You know you have a good reason to be uncertain because you have learned already or can conclude from the data you have seen that this is a region in which the two classes highly overlap. So this is more a case of what we would call aleatoric uncertainty. On the left-hand side here, this is more a case of what we would call epistemic uncertainty. Important remark, which is often a bit overlooked in the literature, is that the uncertainty does not only depend on the amount of data the learner has seen so far, but also on the assumptions it is actually starting with, the underlying model assumptions. So for instance, if the learner makes the assumption or has good reason to assume that the two classes can be separated by a simple linear model, then even in this case here, it will be relatively certain that the true class is positive and not negative, because all the models that fit the data more or less well will give you positive as a prediction. If the learner weakens its assumptions and also allows to fit nonlinear models, for example, quadratic discriminant functions also, then the case is again less clear, because some of the models compatible with the data will say positive, others will say negative. This is also intuitively quite clear, because the more assumptions you start with, the more you can learn from the data, the more actually the data is telling you. And the uncertainty also depends on various other things. So the point I would like to make here is that representing and quantifying uncertainty can't be done without clearly specifying your underlying assumptions you start with, you take for granted. It's just the same as if you want to come up with certain bounds on generalization performance and so on. You always have to make assumptions. So here is another assumption or another example. So suppose you have seen this data here, some positives, some negatives, and you have to make a prediction here at the green point. Under the standard assumption that we are in a closed world, meaning that there are only these two classes, we are in the realm of binary classification, the learner will probably be quite certain that this is a positive point. It's maybe not the most prototypical positive point, but it's clearly on the positive side, so it would be a little bit weird if that was a negative point. However, if we give up this closed world assumption and we assume maybe that new classes may emerge over time, we do class incremental learning, or we allow for out-of-distribution data. Yeah, this is also currently an important topic. Then you are again much more uncertain, because now it's not clear, is that really a positive example, or is it maybe a third new class that you haven't seen before? Okay, so now from a machine learning perspective, I hope I could convince you that it makes sense to do this distinction, and maybe to not only train models that deliver probabilistic predictions, but maybe models that are more uncertainty aware and produce something I called second order prediction on one of the previous slides, on the rightmost image on this slide with the three triangles. So how could we do that? I mean, how could we obtain predictions of that type? How could we obtain this type of second order prediction? Various methods for that purpose have been proposed in the recent literature. I don't have the time to present them all to you here. I also don't have the time to go into technical details, but I try to group them a little bit into three categories, and would now just like to give you the rough idea. So what is the basic idea? So, as I said, we are mainly interested in predictive uncertainty. That means we are here in the realm of supervised learning. You can, of course, also look at other settings of machine learning and try to represent, quantify uncertainty and so on. Here we are in the realm of supervised learning, and we are mainly interested in predictive uncertainty. So given a query instance X, we would like to have a predictor H, which does not only predict probability distribution over possible outcomes Y, but which predicts more, a second order representation, which I denote here by this capital Q, which adequately represents the learner's uncertainty about the ground truth probability of Y given X. And this capital Q, as I said before, can take different forms. The most common in the literature is a second order probability. So Q is a probability over the probability distributions on Y. Another option is a creedal set, a set of probability distributions. These are the two most common used representations in the literature. Okay, so, and I would like now to distinguish these three approaches. The Bayesian approach, what I call validation and self-assessment, and what I call here direct uncertainty prediction. So you could do Bayesian machine learning, you could do Bayesian inference, because the Bayesians, in a sense, they have always been dealing with this type of second-order uncertainty. If you recall how Bayesian inference or Bayesian machine learning is done, then you will probably remember what a Bayesian learner is doing is not just picking one predictive model, one hypothesis in the hypothesis space, but it's maintaining a probability distribution over the entire hypothesis space. In our case, for example, a probability distribution over the set of predictive models. It starts with a prior, and given data that it observes, it turns the prior into a posterior. Yeah. Here, the probability of H given the data D. When it has to make a prediction for a query instance X, this posterior on the hypothesis space turns into distribution over the possible predictions, and if every predictive model, so every H here, is a probabilistic predictor, what we obtain is a probability distribution over the possible probabilistic predictions. Yeah? So this distribution is just the image of that distribution under this mapping here of and this second order distribution here clearly tells you something about the epistemic uncertainty of the learner. If that distribution is very peaked, the learner is quite sure about or pretends to be quite sure about the ground truth probability. If that distribution is more flat, the learner seems to be less certain. If you want to have not this second order distribution, but a precise prediction, this p hat here, what can you do, or what do the Bayesians do? They do model averaging. So basically you take the expectation of that distribution and you obtain your p hat. But then you lose information, of course. You somehow throw away your information about the epistemic uncertainty, which you can really take from this distribution here. So we basically have the aleatoric uncertainty on this level 1 here, the epistemic uncertainty on this level 2, and if you want to call it level 0, we have then the real outcome, whether we observe, for example, positive or negative. So the Bayesian approach is very nice in this sense because it inherently captures this notion of epistemic uncertainty. The drawback of the Bayesian approach is that it's normally computationally intractable. Yeah? If you want to learn complicated models in a complicated space, if this here, for example, is a space of neural networks, it's really hard to maintain a distribution over that space. Yeah? It's becoming computationally intractable. So what people are a lot doing these days is to replace the Bayesian approach by ensemble learning methods. Yeah, maybe you heard about these ensembles of deep neural networks and so on, which are currently quite popular, with the basic idea that, or the hope, let's say, that if you train an ensemble of different models, then this ensemble will well approximate this ground truth distribution here, and if you collect the predictions made by these ensemble members here for a given query instance, the frequency distribution that you obtain will somehow approximate your posterior predictive distribution, yeah, that you have seen on the previous slide. Okay, so these ensemble methods are currently quite popular. The second direction to go is what I call direct uncertainty prediction here, and what I mean by this is the following. You could think of the idea, maybe it's not so unnatural from a machine learning point of view, to skip this detour that is made by the Bayesian approach. What I mean by detour is that you maintain or learn a probability distribution over the model space, and then when you have to make a prediction, you turn it into a posterior predictive distribution on the outcome space, on the space of probabilistic predictions. You could try to do it in a more direct way and train a predictive model, for example, a neural network, which directly delivers as a prediction such a second order distribution. Not just a single probability. This is what you typically do when you train a neural network. You minimize cross-entropy loss or whatever, and the neural network gives you a probability. For example, 0.8 on my first slide. Now, imagine we would like to have a neural network which directly predicts such a second order distribution. One way to do that, for example, is to parameterize the second order distribution, to work with a parametric family of such distributions, for example, Dirichlet distributions, which are distributions on the unit interval, so they are quite convenient when you want to predict probabilities in the binary case. And these Dirichlet distributions here, you see, they are parameterized by two parameters, alpha 1 and alpha 2, or alpha 0 and alpha 1. And by taking different values for these parameters, you can produce different shapes, different types of distributions. The larger the parameters, the more peaked the distributions becomes, and the closer they are together, the more symmetric the distribution is. Yeah, for 1, 1, you obtain the uniform distribution. Here, for example, you will see the distribution for 3, 12, and so on. So, in principle, this could work. But the question is, of course, how do you train such a second order predictor? So from a machine learning point of view, I mean, the standard way to go when you train a machine learning model is to do empirical risk minimization or variance of that, maybe doing some regularization and so on. But what you typically try to do is, given a loss function, you try to find a model within your model class, your hypothesis space, which minimizes the sum of the losses on your training data points. Now, if we want to train such a second order predictor, then what type of loss function do we need? We need a loss function that is able to compare ground truth outcomes, let's say positive, negative in the case of binary classification, with second order predictions. Here this h of xi. So there's a second order prediction. And this is why I call this loss function here L2. So we need basically a loss function, L2, which compares an outcome, an element of the outcome space y, with a second order prediction, a probability over the probability distributions of y. And that doesn't seem so obvious how to do that, right? And the question is, are we able to train a predictor that represents its epistemic uncertainty in a somehow faithful way? It's also not exactly clear what we mean by this. This somehow needs to be formalized. What is a meaningful, what is a good second order prediction actually? What do we understand by this? So does such a loss function L2 exist? So that if we minimize the loss on the training data, we obtain such kind of faithful prediction. And interestingly, this is a problem that we and also others, but also people in my group have recently been working on. And theoretically, we have obtained negative results. So we could prove that that is actually not possible to do. This cannot work. This whole approach cannot work. Although you find quite a number of papers in the literature doing it and also reporting good empirical results and so on. But if you look at it from a theoretical point of view, it's very debatable And yes, we also have theoretical negative results showing that it actually cannot work. I don't have the time here to go into that much detail. This is technically a little bit more difficult to explain, but I just wanted to note. The approach has a good motivation actually, because for first order predictions, if you want to train a probabilistic predictor, it's well known that you can incentivize the learner to predict ground truth probabilities by choosing proper loss functions, which are called proper scoring rules in this case. So if you choose as this loss function L1 here, which compares an observed outcome with a probabilistic prediction, if you choose a proper scoring rule, then you are doing a good job. You are exactly doing the right thing. You incentivize the learner to predict the right probabilities. And so it's a quite obvious idea to say, okay, if it works on level 1, why shouldn't it work on level 2? But it doesn't apparently. Okay, this is theoretically quite interesting. Yeah, this is what I just said. On the second order, it doesn't seem to work. Okay, so finally, a few words on this approach that I call validation and self-assessment. What I mean by this is that the learner somehow, after having been trained, assesses itself and tries to get an idea of how good its predictions actually are, and then either tries to quantify this accuracy or to correct somehow itself. So it's that the learner, in a sense, looks at itself from a kind of meta level. And the simplest approach of that type, you are probably all well aware of, is when you do, for example, cross-validation in order to estimate an error rate. So the learner, for example, could figure out by doing cross-validation that it's making a mistake in 20% of the cases or so. This is an uncertainty quantification, and it's probably helpful, it's better than nothing, but it's also not exactly what we want. Why? Right? Because it's again not a per instance estimate, it's a global estimate of performance. Once again, if you are a patient and your doctor makes a diagnosis and says, I am right in 80% of the cases, you would actually prefer an estimate that is tailored to your particular case and not averaged over all patients that the doctor is treating, right? These per instance estimates, they are actually very difficult to obtain. And again, theoretically, you can show that it's a hard problem, and unless you make some additional assumptions, it's again not really doable. But okay, under some regularity assumptions and so on, of course, you can do a little bit. What I quickly wanted to introduce to you here is conformal prediction, which in my opinion fits quite nicely this what I call self-assessment approach. And conformal prediction is a method that has recently gained some popularity in the literature. So conformal prediction is a framework of reliable prediction that is rooted in classical frequentist statistics and hypothesis testing, and from that point of view, it is somehow a bit orthogonal to the Bayesian approach. Yeah, it's completely non-Bayesian. It's frequentist. So what conformal prediction is doing is, and this is a little bit different from what I have been talking so far about, it's a different way of representing uncertainty. It's training a predictive model which delivers set-valued predictions. So subsets of the outcome space Y. Here is an example. Imagine you train a predictive model that classifies handwritten digits, and given an input like this here, the learner is maybe or should perhaps be uncertain, and it will not just predict one digit, but it will give you a prediction set like here, 2, 3, or 9. And the semantics is, or the idea is that the learner is quite certain, it's not certain which digit it is, but it's quite certain it's one of these. So it's either 2, 3, or 9 with high probability. And this probability actually can be controlled by the user. You can give a certain error bound, epsilon, to the conformal predictor as a parameter, and the conformal predictor will make sure, and this is a nice theoretical property, it will make sure that, at least on average asymptotically, the number of invalid predictions it makes, meaning set-valued predictions that do not cover the ground truth, is bounded by epsilon. It's smaller equal epsilon. This is guaranteed by the learner. The key idea of conformal prediction is, given an instance x for which it has to make a prediction, it hypothetically puts every possible outcome y, and then tests a hypothesis that this outcome is the real outcome. So for example, having seen some digits, zeros, ones, twos, and so on, and having to make a prediction for this red circle here, it hypothetically puts a 0 there, and somehow tries to quantify how strange or non-conform that hypothesis is. And you see that it might be a bit strange to see a 0 over there, right? Given the data that you have seen so far. It hypothetically puts a 1, it hypothetically puts a 2, and so on and so on. The 2 looks actually quite conforming to the data we have seen so far, right? So, so it puts every y hat here as a candidate and sees or tries to quantify how much that conforms to the data. And this nonconformity, formally it is measured in terms of what we call a nonconformity score, or and this is delivered by this f here, which is called a nonconformity function. So what you need is a nonconformity function that somehow tries to quantify how non-conforming the y hat is with the x, if you couple the two together, how strange that y hat actually looks, yeah, as a prediction. You can take whatever non-conformity function you want. Conformal prediction will always deliver you the guarantees. However, the better, so to say, the more suitable that non-conformity function f is taken, the more precise the predictions will be. So the smaller the sets, the prediction sets will become. Yeah? So this is what we call the precision of set-valued predictions. The better the f, the more precise the predictions become. Okay, so this is called a scoring function. This function f here assigns a score to every candidate outcome y hat given the x as a query instance. And what conformal prediction is doing, at least in its inductive version, the original version of conformal prediction that was proposed in the beginning was doing inference in an online manner and was basically doing transductive inference. What is mostly used today is the inductive version of conformal prediction, and what conformal prediction is basically doing is the following. It takes away some part of the data which it uses after having trained a model as calibration data. And on this calibration data, it finds an upper, let's say an upper bound alpha 0, so that for all the real data points, x, y, it has seen in the calibration data, the probability that the non-conformity exceeds this alpha 0 is smaller equal epsilon, or the probability that it remains below is greater equal 1 minus epsilon. And given such an alpha 0 threshold, given a new query, then it can construct a prediction set by including all the candidate predictions y hat, which do not exceed this alpha 0, and it excludes those which look too strange in a sense because they exceed this threshold. So you see this illustrated here. You have seen some, this is your calibration data. And on the calibration data, you basically find out that all the real data points have a non-conformity of at most alpha 0 with a high probability. This is basically, in a simplified form, how conformal prediction is working. So I will skip this part about uncertainty quantification because I see my time is running out, and I would leave a little bit of time for questions. Uncertainty quantification basically is about the idea of quantifying in terms of a single number how uncertain a learner is and how much uncertainty is included in the prediction of a learner. Like Shannon entropy, you know, maybe for probability distributions. This is often useful to have these numbers. If you want to do, for example, active learning or whatever, it's often useful to have these quantitative measures. And again, as a spoiler, and it's not a spoiler because I'm not going to speak about this in detail, but again, this is not an easy problem. This is basically the message I wanted to convey. Okay, so to summarize, I hope I could convince you that learning reliable predictors is actually quite an important topic these days because machine learning is used nowadays in so many safety critical applications. Distinguishing between different types of uncertainty, notably this aleatoric and epistemic uncertainty I mentioned, is probably also not a bad idea, but it's not so easy to do actually. It's not so easy to train machine learning models that represent this second order uncertainty in a really faithful way. And this is a topic of ongoing research. And apart from that, there are various other things, of course, you could address. Things like, so what about model uncertainty if we are not even sure what is the right underlying model class and so on. In generalized settings such as OOD data and so on, I think we will hear about this in another keynote talk. This uncertainty quantification is certainly an important point. How to evaluate such predictors is still a little bit unclear. Other forms of uncertainty and of course how to use that in applications and so on and so on. Okay, and with this I would like to stop. Here is a couple of references I used in my slides. And I would like to thank you very much for your attention, and I'm open to any questions you may have. So thank you very much.
Okay, thank you very much for a very interesting talk. So now we have time for questions. Okay, so here's the first one.
I have two actually if I can. So the first one is about this direct uncertainty prediction, this L2 loss. Yeah, so you said that some people like proven that it is not theoretically possible, but some other people have done some experiments and the results are actually promising, yeah? So I want to ask with what kind of models they tried to do this, if it is possible for just some, if they were simple or maybe complex models.
Basically all these things have been done with deep neural networks, which is the most popular type of learning methods these days. And there are different approaches, but what has been done most commonly is to work with these Dirichlet functions I have shown you before, to define, this is, by the way, also, of course, a critical question. So how do you actually define this L2 loss here? And one approach that has been made in the literature is to start with an L1 loss, like cross entropy, for instance, and given a second order distribution, Q, capital Q, as a prediction, to define the L2 loss as the expected L1 loss, where the expectation is taken with respect to your second order prediction. So it's a kind of average L1 loss. Plus, and this is not an unimportant detail, these methods are typically equipped with a second part, which is a regularizer, and which penalizes predictions that deviate from the uniform distribution, so that incentivize the learner to stay to the uniform. And for this particular type of predictors, we could show that theoretically, they should, if you omit the regularization part, they should converge to a Dirac distribution. Yeah? This has to do with the convexity of the underlying L1 loss. And it's only the regularizer that and this is of course not what we want, because a learner that predicts a Dirac distribution is pretending full certainty. It's certainly not a faithful second order representation. The only thing that prevents it from doing so is the regularizer, but in a sense this is a little bit cheating, right? This is one approach. There are 2-3 others that have been proposed in the literature about which we can say similar things, but yeah, this is basically the way it goes.
Thank you. And the next one about conformal prediction, like it seems to still be like a closed word assumption, yes? That we just compare to classes we know in our data. And I wonder if we could use maybe some generative models that like model the distribution of input to like reject some instances that are just not possible. If we come back to this introduction, like 2 photos, probably model just hasn't seen this data, and we have some other model that just would tell this data is not possible, then maybe this would work. Are those approaches tested, or?
Oh, this is a very good question. I can't tell you spontaneously. You are right. I mean, it's true that conformal prediction is making a kind of closed world assumption. I don't know to what extent conformal prediction has already been combined with generalized assumptions. For example, has been used in the setting of OOD data. It's a very good question. I haven't seen anything so far, which doesn't mean it does not exist, but I haven't seen it. What is interesting maybe to note is that conformal prediction can also deliver the empty set as a prediction. Yeah. It's often doing so in order to get as close to this desired epsilon misprediction rate that is given by the user. And this looks a little bit stupid at first sight, right? Because if you predict the empty set, you know you are wrong for sure. Yeah, it's still doing that, and it's still also a little bit puzzling to me. For example, how could we semantically interpret the empty set prediction, and what, for example, differs? What is different between the empty set prediction and the prediction of the entire set? Yeah, it's not so clear to me either. Maybe it has a little bit also to do with that question, but I don't want to say anything wrong here. It's a very good point. I'm not so sure.
Any more questions?
Thank you very much. Yeah, so I have a question about your ending of your presentation, so out of distribution data. So obviously you can have these models that have this nice uncertainty quantification, but then we have some new data that can be very wrong in a very confident way. So it's obviously super hard problem. But yeah, the question is about what do you see here as the future? Do you think that this problem is almost impossible to solve, or maybe there are some interesting avenues to tackle this problem?
Yeah. This is again a very interesting and challenging question, because what I said and what I tried to emphasize also in the beginning of my presentation, it's virtually impossible to do meaningful uncertainty representation and quantification without taking certain assumptions for granted, which you do not question anymore, that actually allow you to come up with these representations. The problem with OOD, with this OOD data scenario and so on, just like, for example, with anomaly detection, etc., which is a bit related, is that there are no clear assumptions. You say, oh, maybe there comes a new class, but you don't have any clue, for example, how that may be distributed in and how that distribution may deviate from the distribution of your in-sample data, and how probable it is that a new class emerges, and so on. And I am pretty sure, we didn't look at this problem that much so far, but I am pretty sure that it's not possible to come up with meaningful representations unless you are able to make meaningful assumptions. And this in turn is very hard to do, because it's in the nature of the problem to say, oh, open world, anything may happen. And if you say anything may happen, then how do you quantify that? And how do you actually make meaningful assumptions on that? It's a really, really hard problem. And what I have seen so far in the literature, I have to say, on this OOD data stuff and so on, doesn't convince me that much. I have to say, from a theoretical point of view, I don't exclude that there is progress possible, but it's a really hard problem.
Thank you.
Thank you for an amazing talk. I was wondering, because all the methods you mentioned somehow include in the process of quantifying uncertainty y, but looking at your images, one can think that you can actually reason about the uncertainty just by modeling the distribution of x's. And so my question is if there is also some kind of line of the research in this area. So as addition, having a classifier, you also have maybe additional method that estimates just the distribution of x's, and based on that tries to reason about uncertainty.
Yeah, exactly. There are. So maybe my talk gave a little bit the impression that most of the methods in that field are still standard discriminative learning methods, but this is not perfectly true. You are right. There are also generative models that are used. So, for instance, you train a one-class predictor on the zeros. You train a one-class predictor on the ones, and so on. So you basically try to learn the conditional distribution of x even y. And then given a new x, you basically check whether it's well covered by any of these distributions or whether it's somehow lying outside. And every conditional distribution of x given y gives you a low density. Yeah? So this is a common approach, especially useful when you learn with very expressive model classes such as neural networks and so on, because then you can really argue that the epistemic uncertainty is specifically high in regions that have a low density everywhere. And yes, good point, you are right. Didn't mention that here, but you can also go that way and train generative models and use that for uncertainty representation.
Okay, maybe we have time for one more question. Okay.
Actually two, but very, very short one. So one is very specific. I think in one of the early slides you shown a picture which was confirmed by a network, and you told us that this network was like 80-something% sure about recognizing this picture, I think. So my question concerns the interpretation, like on which basis actually have you made this inference? Is it some kind of post-processing of a weights or Hessian, or how do you actually state it? Yeah. So this is the first question.
Yeah.
And the second one is a bit more general, because when I've been listening to your presentation really carefully, I hope, and you've been discussing a lot about uncertainty. And in general, when I hear about uncertainty, I think about the distribution and statistics, etc. And originally, traditionally, machine learning was very opposite to that, because you had the idea of the training, and the prediction was basically everything that you cared about, yeah? Like in traditional machine learning, which was opposite to statistics, where people always used to look at the distribution, and when evaluating prediction, the distribution and the percentile of actually the fit was what was reported on. So do you think that this stream of research is pointing at the situation that machine learning is starting to incline in the direction of statistics in terms of evaluating the predictions and kind of, you know, like old school Monte Carlo experiments around network that actually you can approximate the distribution and you know, these ideas? Do you think that that's happening now, like in this stream?
I would say so. So to start with your second question, I would definitely say so. We have a clear development, let's say, or a movement of machine learning more towards statistical methods, and there is also nowadays this notion of statistical machine learning. Yeah. So the connection is very close, and it's becoming closer and closer. And in my opinion, this is a meaningful development because this is about data analysis in a broader sense. So clearly machine learning and statistics have a lot to do with each other. And you are right, statisticians have looked at these uncertainty quantification problems already from the very beginning. For them it is more than natural to do so. Yeah, exactly. Yes, this development is very visible. It has already been visible since many years now, and it's becoming more and more visible, I would say. For me, it's a good development. It's the right direction to go. So I'm a fan of statistics, but maybe I'm not completely unbiased here, but yes, I think it's a good development. Regarding your first question, where does this probability come from? So this is just an example. I mean, there is not even a real predictor behind. I just took it for illustration. But these probabilities that are delivered by standard neural networks, for example, these days, they are obtained as a prediction of the neural network, which has been trained, for example, to minimize loss functions such as cross-entropy loss. And cross-entropy loss is an example of, I don't know whether you remember, I mentioned these proper scoring rules. It's an example of such a proper scoring rule. So theoretically, you know that if you minimize empirical loss by using cross-entropy error, you train a predictor which theoretically or asymptotically predicts the ground truth probability, given it has enough expressive power. So therefore, there is a certain legitimation to consider this as a meaningful probabilistic prediction. Even if in practice we have these biases and so on, what I also mentioned here. But this is the way these predictive classifiers are normally obtained.
But if you bootstrap the input set, would you kind of obtain the same theoretically? If you bootstrap the input set and then you let the network train and then you get the prediction, you could potentially do the same, yeah? And just to get the distribution of the output, yeah? So that would lead in theory to the same outcome.
If you bootstrap the input set and you average in the end, or probabilistic predictions, I don't know, but I'm pretty sure that the guarantees will carry over, at least an expectation, yes. Yes.
Thank you.
And hopefully you will reduce variance and so on. Yeah.
So we are 10 minutes past the break time, so unfortunately we need to stop here. So let's thank the speaker again.